Hello all and welcome to my channel. This is Valentino and today we are going to go over a mechanics M2 paper from January 2026, and this is the A version. Okay, so you can see that A letter over there, which means that this is a backup paper that most people never see, I believe, because this is a paper that Edexcel puts out there in case there is a leak or something like that. Anyway, it's good practice material, and today I will just dive in and start. Okay, so I mean, I usually say a few things, but today I'm not because I want to finish this a little bit fast and for a change. So, question one asks a particle P of mass 2 kilograms is moving with velocity 3I hat plus 4J hat meters per second when it receives an impulse. And those are your unit vectors, okay? Immediately after the impulse is applied, P has velocity 2I hat minus 3J hat meters per second. Question A asks to find the magnitude of the impulse. So I'm going to create a clean page so it can work. And let's start with question one. So impulse, as we know, is equal to the change in momentum, okay? And impulse is a vector, okay? Because it depends on velocity, therefore, and velocity is a vector quantity. So therefore, impulse is a vector quantity as well. So the change in momentum is going to be equal to the mass of the particle times the change in speed, right? Which is equal to the mass of the particle times the final velocity minus the initial velocity, right? So we will just plug in the values. So the mass is 2 kilograms. The final velocity is 2I hat. That's how I write the unit vectors out of habit. So I put a hat, meaning that the magnitude of this vector is 1. Okay, and you can also have any type of unit vectors, right? I mean, if I write this, it is immediately implied that whatever the vector A is, that's the unit vector A that points in the direction of the A vector and has a magnitude of 1. And then the A vector is equal to A hat over, A hat is equal to the vector over its magnitude, okay? So anyway, this is perhaps too much and not needed here. So let's write again. So 2I hat minus 3J hat minus the initial vector, velocity vector, which is 3I hat plus 4J hat, okay? And we just have to compare components. So this goes with that, and then this goes with that. So we have 2 times minus I hat minus 7J hat, okay, which means that the impulse is finally minus 2I hat minus 14J hat kilograms meters per seconds, right? Just like momentum, I mean, the units are the same. And the question asks for the magnitude of the impulse, right? So the magnitude, of habit, I used hat again. So the magnitude of I is the square root of minus 2 squared plus minus 14 squared, which yields the root of 200, which can be written as 10 root 2, right? Kilograms meters per second. Okay, this is part A. Now let's read part B. Find the angle between the direction of the impulse and the direction of motion of P immediately before the impulse is applied. Okay, let's use a clean page again. So this is part B. So the direction of I of the impulse is what I was mumbling about earlier. So the direction of motion of I is the unit vector I hat, which points in the direction of I and has magnitude of 1. Therefore, it's equal to the vector itself over the magnitude of the vector. I haven't checked the mark scheme. I hope that this is okay to solve this way. Okay, so this is 1 over 10 root 2, and then minus 2I hat minus 14J hat. Okay, so this is the unit vector that points in the direction of the impulse. And then the direction of VI, right? Because this is what they are asking us to do, to compare the direction of the impulse with the direction of the initial velocity, okay? So similarly, we will do exactly the same. So the unit vector in the direction of the initial velocity is equal to the initial velocity vector over the magnitude of the initial velocity vector. And since the initial velocity is this one, right? Let's use red. So that's the initial velocity. So its magnitude is the hypotenuse of a 3, 4, 5 triangle, right? Because I hope that's clear, right? So maybe I can write it. Okay, it's the 1 over the square root of 3 squared plus 4 squared, and then 3I hat plus 4J hat, which is nothing but 1/5 times 3I hat plus 4J hat. Now, how do we find the angle between these two? The cosine of theta is simply the dot product between I hat and VI hat. How do we know that? Because if you have this vector, let's say I hat, and then this vector VI hat, okay, the angle between them is the dot product, pretty much, okay? Right, do I have to explain anything else? If I do, I mean, if this doesn't make sense, ask me in the comments and I will provide more explanations, okay? Actually, maybe, okay, to prove this, okay, don't want to be sloppy, because I tend to be sloppy sometimes. So if you have I, the vector I, and the vector v, and they have an angle theta between them, then cosine of theta is I dot is v over the magnitude of I times the magnitude of v. But in our case, we just calculated this, and we called this I hat, and we calculated this, and we called it v hat. Okay, so vi hat, whatever. So the cosine of theta is the dot product between the unit vectors that point in the direction of the vectors you are interested in. Anyway, cosine of theta is then I hat dot vi hat, so 3 over 5 times minus 2 over 10 root 2 plus 4 over 5 times minus 14 over 10 root 2, right? So if we carry on this calculation, I'm gonna just provide the final result because I ran out of space. So that's minus 0.87. Therefore, theta is gonna be in the third quadrant, right? The second quadrant. So 150.45 degrees. All right, so this was question 1. I hope it makes sense. If it doesn't, let me know in the comments. And we will jump to question number 2 now. Okay, question number 2. A cyclist and his bicycle have a total mass of 75 kilograms. The cyclist is moving up a straight road inclined at an angle theta to the horizontal where sine of theta is 1 over 21. The non-gravitational resistance to motion is modeled as a constant force of magnitude r newtons. The cyclist is working at a constant rate of 280 watts and moving at a constant speed of 2 meters per second. The first question is to find the value of r. Okay, let's create a clean page again. So this is our problem 2, question A. So I'm gonna draw a scheme Usually when I make an introduction to my videos, I talk about various things that I find important when solving these papers. So since I haven't made that introduction, I'm just going to mention here that in the mechanics papers, I think that is really important to draw a really good scheme about what's going on in most problems, not all of them. Okay, so in this case, we're gonna model the bicycle. I was gonna say the motorcycle. I think it's a bicycle, right? Yes. So we're gonna model it as a box. Okay, that is going up the incline. Okay, that's theta. Okay, and let's draw the free body diagram. I'm gonna use red. So that's the center of mass of the bicycle, say. Okay, so the weight points down. So okay, so that's the weight, points down. The reaction force points up. So that's the reaction force. The resistive force is modeled as a constant force R that opposes the motion. Okay, so the motion is in this direction. Okay, and then we also have the force. Wait, was it the motorcycle after all? Because we have the okay, let me read it again. A cyclist and his bicycle. Okay, the cyclist is working at a constant rate. Okay, so this is the force provided by the cyclist, which is going to be equal to the power over the speed he or she is going. Okay, and I'm going to explain it further in a while. So these are all the forces, right? So since the direction is along the incline, we are going to analyze the weight into a component that is perpendicular to the incline, a component that is parallel to the incline. Okay, so this angle is going to be theta, and the reason is that I always explain it as follows. So this line is perpendicular to this line, and then this line is perpendicular to this line. Okay, so the inscribed angle is theta, therefore this angle is going to be theta. Okay, so that's how I always explain this. Okay, let me remove those lines. Okay, perfect. So this component is going to be weight times cosine of theta, and then the component that is parallel to the ramp is W sine theta. It's already complicated. Okay, so the velocity is constant, which means that the acceleration is 0. Okay, so along the incline, we have that the force from the cyclist minus the resistive force minus the weight sine theta. So the sine theta component of the weight should be 0, right? Therefore, the force that we are looking to find, the resistive force, is P over V. Okay, so I said I was gonna comment on this. Actually, okay, let me erase this and say that power is the force times the velocity the cyclist is exerting on the bicycle, right? And how do we know this? Because force is in newtons, and then velocity is in meters per second. So newtons times meter is joules over seconds, which makes watts. Okay, so let's replace. So the resistive force is going to be the power by the cyclist over the velocity minus mg sine theta. And now we can plug in values. So 280 watts over 2 meters per second minus 75 times 9.81 times over 21, since sine theta is 1 over 21. And the final result is 104.96, which is about 105 newtons. Okay, so this is our answer. I hope it makes sense. The trick here is to analyze the forces correctly and then realize that if the velocity is constant, then the acceleration is 0, and we can balance forces and find the result we want, which is the resistive force in this case. Okay, there is a part B, so let's create another clean page for part B, and let's go read part B now, okay? Okay, part B starts right there. Later, the cyclist cycles down the same road on the same bicycle. He's again working at a constant rate of 280 watts, and the resistance to motion is now modeled as a constant force of magnitude 60 newtons. Okay, so they changed that. Find the acceleration of the cyclist at the instant when his speed is 3.5 meters per second. Okay, let's go do this. Okay, let's design the ramp again, the incline. Okay, so this is a new scheme. Don't use the same scheme. It might confuse you. It's good to have separate things, doing work for separate problems. Okay, if that makes any sense. Okay, again, this is our bicycle. Let's draw the forces. The first thing we need to do. Okay, so the weight, uh, the reaction from the floor that we don't really use in this problem, but whatever. Okay, it's for completeness. Then we are told that the cyclist moves down now. Okay, and he has some velocity that changes with time this time. Okay, because he's accelerating, so there is an acceleration downhill. Okay, in the direction parallel to the incline. Okay, so we have a resistive force as before, so that's R. And we also have the force from the cyclist like before, so that F, which is equal to P over V. And we also have the, let's call it the kind of like the X component of the weight, but it's not really the X component because the axis is tilted. But nevertheless, this is weight times sine theta. This angle is theta, and for completeness, this component is W cosine theta. Okay, now the situation changed. Now, since the acceleration is to the left, then all the forces that point to the left are positive. So P over V minus W sine theta, plus W sine theta, excuse me, minus R is equal to MA. Okay, and we are told that we need to find A when the velocity is, what do they say? I think 3.5 meters per second. Let me see. Yes. So we solve for A. So A is P over V plus W sine theta minus R, right? Yes. Over the mass of the bicycle plus cyclist system. Okay, when I work out problems, I like to reach a final algebraic expression usually, so this one. Okay, and then I plug in the numbers. Okay, so we need the acceleration when the velocity is 3.5. So we have 280 over 3.5, and this is the fraction right there, plus 75 times 9.81 times 1 over 21, which is the sine, minus 60 newtons this time, so over 75. So this yields, okay, so the final result is 0.73 meters per second square. Okay, so beautiful. This was problem 2. Let us move on to question number 3 now. Question number 3. The uniform lamina OABCD is shown in figure 1 with OA equal to 6A, AB is 3A, CD is 2A, and DO is 6A, and with right angles at OA and D. So question A, find the distance of the center of mass of the lamina I from OD and 2 from OA. So pretty much we consider O to be the origin, and therefore we need to find the X and Y centers of mass of the lamina. Okay, so let's create a clean page. So this question 3, part A. I have to admit that working on laminas took me many years back. I actually never learned this in high school. I took a class in actually 4 classes now that I think about it. So my story is a little bit unconventional. I mean, my studies, because I went to an engineering school, but I studied applied physics and applied math. So I didn't really go to physics school, okay? And there I took the concentration of applied physics eventually. But anyway, the story is that I had to take 4 mechanics classes, and those were mechanics classes that engineers took, people who become civil engineers, etc. So I learned about center of mass concepts there. Okay, and so this was more than 20 years ago. Okay, so working on these problems took me way back. Okay, so meanwhile, while I was telling you the story of my life, I'm also uh, designing the lamina. Okay, so that's 6A, that's 2A, that's also 6A, this is 3A. Okay, so we're gonna divide the lamina into pieces 1, 2, and 3, and you will see what I mean. Oops. So, okay, this is the first piece, which is a rectangle pretty much, right? And so this distance, I mean, I don't really have to say it, but it's 2A. Okay, and then we will create a triangle right there. Okay, so I'm gonna name this as 2. Okay, so that's 2 is another rectangle, and then 3 is a right triangle, and it's actually, let me see, okay, so this is 3A, so this is 4A, so therefore this is 5. Okay, so the mass of object 1, actually, okay, so mass of object 1 is 12A squared. How do I know this? Because 6 times 2, 12A squared. Okay, then the mass of object 2 is also 12A squared, because this side is 3A, and this side is 4A. So 4A times 3A is 12A squared. And then the mass of object 3 is 1/2 times 4A times 3A, so 6A squared. And the total mass is going to be the sum of all this, so 30A squared, because we have 12 plus 12, 24, plus 6, 30A squared. Okay, sadly, we will have to turn another clean page, okay? When I will become rich from YouTube and from these videos, I will probably move to either a super big screen, like a super large iPad. I don't know how large the largest iPad is, or even better, rent a room somewhere and have a whiteboard and have someone filming me, etc. So, but for now, I'm not rich yet. So, guys, please subscribe so I become rich. So I have the ability to make not the ability, the resources, because I do have the ability, but I need the resources to make better videos, so I have more space and stuff. Okay, so for object 1, okay, the center of mass, so center of mass, we call it as com, is at point A, 3A. How do we know this? It's the intersection, right? I mean, of the diagonals. It's a rectangle, right? So the center of mass is right there. So the x coordinate is A, the y coordinate is 3A. I hope this is clear. For 2, let me switch back to black. The center of mass is going to be, okay, before we talk about the center of mass, point E, okay, so this is point E. I forgot to put the letter E there, okay, so point E is at x equal to 2A, and y equal to 0 relative to the origin, which we take as O. Okay, so therefore the center of mass of object number 2 is going to be at 4A, because it's still a rectangle of side, one of the sides is 4A, so 2A plus 2A, it's going to be 4A in the x direction and 3A over 2 in the y direction. Okay, now for 3 we need to do a little bit of work for our triangle. So the F, so the point F, which is this one, okay, so this is our point F. So F is at the coordinates 2A, 3A, okay. Then B, point B, is this one, is at coordinates 6A, 3A. And C, which is that point up there, is at coordinates 2A, 6A, okay. So the center of mass, actually, let me move down here. Okay, so the center of mass is going to be 1/3 times 2A plus 6A. Oops, fix that. So 1/3 2A plus 6A plus 2A, and then the y coordinate is going to be 1/3 3A plus 3A plus 6A. So finally, the center of mass of object 3 is 10A thirds and then 4A. Okay, and we're not done yet. We still have to apply the principle of moments to find the center of mass. It's not really the principle of moments. It's the combination of the principle of moments and balance of forces. But anyway, so we multiply the center of mass of object 1, so A, 3A, with its mass, which is 12A squared, okay, plus the center of mass of the second object, which is 4A, 3A over 2, times its mass, which is 12A squared, plus the center of mass of the triangle, 10/3 A, 4A, times the mass, 6A squared, okay, and this has to be equal to the x coordinate of the center of mass and the y coordinate of the center of mass times the total weight, which is 30A squared. Okay, I hope this is clear. Okay, so A squared goes away. Okay, and we just have to sum A plus, sorry, so 12A plus 48A plus 6 over 3 is 2, so 20A, and then 36A plus 6 times 3, 18A. Please let me know if I messed up something. Plus 24A. This should be equal to x y times 30. And eventually, if you work this out, you find these coordinates for the center of mass. The x coordinate is 8A over 3, and the y coordinate is 13/5 times A. All right, so this was part A. Long but straightforward. I think this was the best way to divide the area, but if you thought of another way, let me know. Okay, so let's go to part B now. Okay, part B starts here. So the lamina is suspended from C and hangs freely in equilibrium with CB, inclined at an angle that's A or alpha. I don't know. I think it's alpha. So inclined at an angle alpha to the vertical. Find to the nearest degree the size of the angle alpha. Okay, so if we hang this thing from C, okay, the whole thing is going to rotate, and this rope is going to be directly above the center of mass. Okay, so finding what's the question again? We need to find the angle alpha. Okay, so the angle alpha is going to be equivalent to, let me erase this. Okay, yeah, there. So the angle alpha, so the center of mass is going to be at G, okay, which is somewhere there, okay, because we found it as 8/3, which means it's more than 2a to the right, and 13/5 is more than 2a up, okay. So so it's somewhere to the right of C, in other words, and a little bit below B, okay. So that's where G is approximately. So the angle alpha is equivalent to finding this. Okay, so this is going to be, if I draw a line from C to G, okay, and this is going to be the angle alpha. Okay, I hope this makes sense, because if we hang it vertically, right? So if I put a string right there and we hang it vertically, then this G is going to rotate and come there, okay? And therefore the angle that this line is going to make with CB, and CB is also going to rotate, okay? So CB is going to be somewhere, I don't know, let me think. So maybe it's going to be there. So if that's alpha, then the alpha I drew with purple is the same, okay? If that doesn't make sense, ask me in the comments and I will try to provide a better explanation. Okay, so to find alpha, we're gonna utilize finding the unit vector in the direction of CB and in the direction of CG. Okay, wait, let me go back to purple. So in other words, we're gonna find CB hat and that's CG hat, excuse me. It's really hard to film these videos, guys, sometimes. So CG hat and that, and then CB hat. Okay, so the dot product between CG hat and CB hat gives us the cosine of alpha. Okay, so let's go find a clean page and solve this. Okay, is there anything else? So, okay, before okay, let me turn the page and we'll take it from there. Okay, so this part B. So basically, I'm just gonna draw C. So the coordinates of C are 2a, 6a. You can check for yourselves. Then we have B. Okay, so B has coordinates 6a, 3a. Okay, and then we also have G. Okay, so this is G that has coordinates 8a thirds and then 13/5 a. Okay, so let's find the vector CB. So CB is going to be 4a, so 6a minus 2a, and then 3a minus 6a. So CB is the vector 4a minus 3a. Okay, therefore CB hat, the unit vector, is going to be 1/5, okay, which is the, okay, I'm going a little bit too fast. So 1 over the square root of 4 squared plus minus 3 squared, which is of course 5, times a squared, right? No, sorry, just a, okay, times 4a minus 3a. So a cancels. Okay, that a outside the square root comes from the fact that we are squaring 4a. So 4a squared is 16a squared, right? So we can take a outside and it becomes an a. Okay, so this is 1/5 4 minus 3. That's the unit vector in the direction of CB. And then now let's find CG, the vector CG, which is 2a thirds and then minus 17 fifths A. Okay, now the magnitude of CG is something complicated. I'm just gonna quote the result to save a little bit of time so you can work this out yourselves. Okay, so the unit vector in the direction of CG is 15 over the square root of 2701, and then 2/3 minus 17 fifths. Okay, so the cosine of alpha, the cosine of alpha is CG hat dot CB hat. So this yields 0.74. Therefore, alpha is 42.03 degrees. Okay, so this was a little bit of a complicated problem, I would say. But if you write the coordinates correctly and you create these vectors and then the unit vectors and dot them, you can find the angle. Okay, so this was question 3. Let's move on to question number 4. Okay, question 4, it states up top that in this question you must show all stages of your working. Solutions relying on calculator technology are not acceptable. Not sure what this means, but okay, let's do it. At time t seconds, where t is larger than or equal to 0, a particle P has position vector r meters with respect to a fixed origin O, where r is given by that expression. At time t capital seconds, P is moving in a direction parallel to the vector minus I hat minus j hat. Find A, the value of t capital. Okay, so let's create a clean page. So this is question 4. So the position vector is t cubed minus 9t squared over 2 minus 24t. Okay, I hat plus the y component, which is minus t cubed plus 3t squared plus 12t, and that's j hat. Okay, so first of all, let's find the velocity. Okay, so the velocity is going to be the first derivative of the position vector. Okay, so we get 3t squared minus 9t minus 24, and this is the I hat direction, plus the first derivative of the y component of the position vector, which gives the y component of the velocity vector, will be minus 3t squared plus 6t plus 12 j hat. Okay, so we are told that v is parallel to the vector minus I hat minus j hat. Okay, which means that the x component of v is equal to the y component of v, pretty much. Okay, because these two are equal. Okay, yeah, okay, I mean, there is nothing else to say, I guess. So we have to set this component and this component equal to each other and solve for t, and that's going to be our capital T, pretty much. Okay, so 3t squared minus 9t minus 24 equals minus 3t squared plus 6t plus 12, right? So we have 6t squared minus 15t minus 36 equal to 0. So t12 is equal to 15 plus or minus the square root of 15 squared plus 4 times 36 times 6, okay, over 12. So we need more space. Okay, so t12 is 15 plus or minus the square root of 1089. Are you not allowed to use a calculator to find that? I don't know. Okay, so 15 plus or minus 33 over 12. Let me know in the comments actually what they mean by no calculator. Okay, so the negative value is rejected because we will get a negative time, which makes no sense. Okay, so t is 15 plus 33 over 12, which is 48 over 12, which is 4 seconds. All right, let's dive into part B now. Okay, part B, find the magnitude of the acceleration of p at the instant, when t, lowercase t, is equal to capital T. So equal to 4 seconds pretty much. So first step, find the first derivative. So a is dv over dt. So we have to find the first derivative of the velocity vector, and that's going to be our acceleration vector. So that's going to be 6t minus 9 I hat plus minus 6t plus 6 j hat, okay, at t equal to 4 seconds. We have that a at t equal to 4 is equal to 15 I hat minus 18 j hat, okay? So the magnitude of a is the square root of 15 squared minus 18 squared, okay, which is the square root of 549, which is 23.43 meters per second, okay? That's quite a large of an acceleration because g is 9.81, right? So this is more than 2 g's of acceleration, so that's a lot. All right, so this was question number 4. So let's move on to question number 5. Okay, question 5. A uniform rod AB of mass M and length 2A is freely hinged to a fixed point A. Okay. Okay, that's the point. A particle of mass k times m is fixed to the rod at B. The rod is held in equilibrium at an angle theta to the horizontal by a force of magnitude F acting at the point C on the rod, okay, where AC is 5 over 4 times A, okay, as shown in figure 2. The line of action of the force at C is at right angles to AB and is in the vertical plane containing AB. Given that tangent of theta is 3 over 4, show that F is 16 over 25 m times g times 1 plus 2k. Okay, I'm going to draw the forces here, okay, and then we will work the problem in a clean page that I will create in a moment. Okay, so at B we have a particle of mass km. Okay, we don't know what k is, so whatever it is, it's going to have a weight k m. Oops. So it's going to have a weight k m g, right? Okay, and then this angle is going to be theta. So this is going to be your angle theta. The reason is that this side's okay. Let me create use a different color. So the reason is that this side is perpendicular to this side, right? And then this side is perpendicular to this side. So the inscribed angle is theta, and so is this angle is theta. Okay, I hope this makes sense. For the geometry, okay, so we can analyze this force into a component that is perpendicular to the rod AB, which is the one we need to calculate moments actually. Oops. Okay, so that's kmg cosine theta. And then, okay, there is a component kmg sine theta along AB, but it doesn't really create a moment, so I'm not going to design it. And then somewhere here is the center of mass. Okay, let's call it G maybe. Okay, so the mass of the rod will point downwards, and then with exactly the same logic as the other weight kmg. This component is going to be mg cosine of theta. Okay, let's now create a clean page and solve this. So this part A, problem 5a. Okay, so before we solve this, let's do a few calculations. Tangent of theta is 3/4, so we can write this as sine theta over cosine theta equal to 3/4. We can use the calculator, but it's a good mental exercise, I guess. So sine squared theta is 9/16 cosine squared theta. So we are interested in the cosine theta, so let's solve that. So 1 minus cosine squared theta, which is sine squared theta, is going to be 9/16 cosine squared theta. Okay, so 25/16 cosine squared theta is 1. So cosine squared theta is 16/25. So cosine theta is 4/5. And since we know what cosine theta is, then sine theta is going to be 3/4 times 4/5 pretty much. So 3/5 is sine theta. Okay, let's take moments about A. Okay, so about this point. Okay, so we will have 2 clockwise moments from the weights and just one anti-clockwise moment that balances them. Okay, which is F, which is the unknown quantity in this problem pretty much. Okay, so we have K M G cosine theta times 2a, which is the distance, okay, plus mg sine theta times a, right, is f times 5a/4. So a cancels beautifully. So let me think. Why did I write sine theta there? Excuse me, guys. This is cosine theta. I don't know what got into me. So that's cosine theta. Okay. So so kmg times 8/5 plus mg times 4/5 is f times 5/4. Okay, so f is going to be 32/25 times kmg plus 16/25 times mg. So we can we can take 16/25 times mg as the common factor, and we are left with 2k plus 1, which is the answer that we have to find. So great, part A is done. Let's create a clean page for part B, and let's go read it, okay? Okay, part B, find in terms of mg and k, I, the horizontal component of the force exerted by the hinge on the rod at A, and 2, the vertical component of the force exerted by the hinge on the rod at A. Okay, we're going to use the same scheme. My bad, but in part A, these are not all the forces, okay, because there is a reaction from, there is also the reaction force from the hinge at A that points in that direction, okay, let's call it R maybe, okay, but we don't take it into account because we took moments, we didn't take it into account, excuse me, because we took moments about A. So it doesn't matter whatever the force there is, okay, it didn't matter for part A. But for part B, okay, we are told that we have to find the vertical and horizontal component of the force exerted by the hinge on the rod at A. So let's call this force V, so the vertical component, and the horizontal component. So together these two make this force pretty much, okay? but we don't care about that now. So, okay, we only care about these forces. Okay, so the horizontal force, H, wait, we also need to analyze, okay, okay, first of all, let me erase a few more things for part B. Since we are interested in the vertical and horizontal components, we don't need these components, okay? I mean, we only need the components that are vertical or parallel to V and H, okay? So, okay, so, oops, let's use black. Okay, and we have to analyze F. We calculated F earlier, right? So we have to analyze it into a component that is parallel to V, okay, and a component that is parallel to H. I messed it up, guys. I'm sorry. Okay, let's try again. Okay, so that's the component that is parallel to V, the vertical component of the force at A, and this component is parallel to H. Okay, so that angle is theta. Y again. Let's see. So this side is perpendicular to this side, and then this side is perpendicular to this side. So if this angle is theta, that angle is also theta. Okay. So I hope you're convinced for that. Let's see. Remove those orange lines. Okay. So this is going to be F cosine theta, and this is going to be F sine of theta. Okay, F sine theta. Okay, so F sine theta is going to be equal to H, pretty much. Okay, so let's go do that. Let's go write that down. So this part I. So H is F times sine theta, or 14 over 125 mg times 2k plus 1. And then for part 2, we have V plus F sine theta F cosine theta. Be careful with the sines and the cosines, guys, okay? So V plus F cosine theta is mg plus k mg, okay? Which means that V is mg plus k mg minus 64 over 125 mg times 2k plus 1. So this is equal to mg, and then 1 plus k minus 64 over 125, that's k, by the way, okay? Minus 128 over 125 times k. Okay, so this is m times g times 61 over 125 minus 3k over 125. Okay, so we found the two components, H and V. That's perfect. But there is also a part C. Okay, let's go back and read it. So part C starts right there. Given also that the force acting on the rod at A acts at 45 degrees above the horizontal, okay, find the value of K. So earlier I was wrong. I designed the force that the hinge acts on the rod at A as being along the rod, but actually now they tell us that this force is actually at an angle of 45. Okay, so ignore what I said earlier. So what they are saying is that this angle is 45. So basically, this tells us that the horizontal and vertical components are equal to each other. Okay, so, and these horizontal and vertical components are the horizontal and vertical components of that force. Okay, so let's go do that. Okay, so for part C, as we said, this component should be equal to this component pretty much. Okay, so 48 over 125 m times g times 2k plus 1 should be equal to m times g over 125 times 61 minus 3k. So m times g cancels, 125 cancels. So we find 96k plus 48 is equal to 61 minus 3k. So we have 99k is equal to 13. So k is 13 over 99. Okay, so that's the answer for part 5. So sorry, for part C of question 5. So we're ready to move on to question number 6 now. Okay, question 6. Two particles A and B of mass m and 2m respectively are moving in the same direction along the same straight line on a smooth horizontal surface with B in front of A. Particle A has speed 3 meters per second and particle B has speed 2 meters per second. Particle A collides directly with particle B. The coefficient of restitution between A and B is 2/3. The direction of motion of both particles is not changed by the collision, so they keep moving to the right. Immediately after the collision, A has speed v meters per second and B has speed w meters per second. Question A, part 1, show that w is 23 over 9. Okay, so let's create a clean page. So this question 6. The scheme doesn't really help here, but maybe a little bit psychologically it's easier when you see it. So there is a before and after, right? So before we have the ball A with mass m moving with velocity 3 meters per second to the right, and then we have ball B with mass 2m moving with velocity 2 meters per second to the right. Okay, so after the collision, we have A moving with velocity v meters per second to the right, and then B moving with velocity w meters per second to the right, and w is larger than v. How do we know that? Because if v was larger than w, then the two particles would collide again, right? Because A would catch up with B again and collide again, etc. So this is not what's happening, and we also know that they move to the right. They are moving to the right, excuse me, which means that W is larger than V, and this is actually key to the problem. So for part A, we will use the fact that E, the coefficient of restitution, is equal to the speed of separation, okay, over the speed of approach. Okay, so let's keep going. So E is going to be W minus V, okay, because as we just said, W is larger than V. And then the speed of approach is 3 minus 2, okay? So in both cases, you have to use the larger, you have to subtract the smaller velocity from the bigger velocity, pretty much, okay? So W minus V is going to be 2/3, pretty much, okay? Also, we have conservation of momentum. So we have m times 3 plus 2m times 2 is equal to m times v plus 2m times w, right? So m cancels in both sides, and we get a second equation, 2w plus v is 7, and we can put it side by side with w minus v equal to 2/3, and we can add these two. So if we add them, we get, let's create a clean page again, we get 3w is equal to 23 over 3. So w is 23 over 9, okay? I think this is, do they quote this result? Don't remember. So anyway, so let's go see what the other question is asking. I think it's asking to find V. Okay, yeah, and they quote this, so 23 over 9. Okay, great. So part 2, find the value of V. Okay, let's do that. So for part 2, we have V is W minus 2/3. Okay, so we get 23 over 9 minus 2 over 3, which is 17 over 9, which is the value of v. Okay, now let's do part B. Part B starts right there. It's a little bit more complicated, I believe. So when A and B collide, they are 3 meters from a smooth vertical wall, which is perpendicular to their direction of motion. After the collision with A, particle B hits the wall and rebounds. The coefficient of restitution between B and the wall is 1/2. There is a second collision between A and B at a point D meters from the wall. Find the value of D. Okay, so let's try to set this up. Okay, part B. So we are told that when they collide, so let's see. So this is the after. I mean, remember this scheme. So this is the after the collision. So anyway, so let me try to explain. Okay, it's going to be a little bit complicated, I think. So this is the wall. Okay, so that's the wall, and we have A and B. So that's A and B. Okay, and this is the moment of collision. Okay, so B moves with a velocity 23 over 9 to the right, and then A, I'm gonna design its velocity down here, even though, okay, so this is the velocity of A pretty much. Okay, so I'm gonna design it down there, and the velocity of A is 17 over 9. Okay, and this distance is 3 meters. Okay, when they collide, then since B is moving faster, it hits the wall and moves back, okay, with a velocity of w over 2 pretty much, because the coefficient of restitution is 1/2. Okay, so it moves with velocity w over 2, whereas A keeps moving with the same velocity of 17 over 9. So it moves with 17 over 9 of velocity, and they meet again at this point, okay, which is a distance d from the wall, and they collide, okay, and we have particle B. So this is going to be your particle A, this is your particle B, okay, and B moves to the left with velocity minus 23 over 18 pretty much, okay, which is 1/2 of its initial velocity. Okay, so let's write all these things down. I hope it's not very confusing, and I hope this is clear. Okay, so B, let's do a few calculations. B rebounds with, okay, I mean, if you want to be formal about it, you have 1/2. The coefficient of restitution is going to be W prime, the new velocity, minus V, the velocity of the wall, over W minus 0, which is the velocity, the initial velocity, right? So W prime is going to be W over 2, or 23 over 18. And it's actually minus 23 over 18 because it's moving to the left. Okay? Okay, time for B to reach the wall will be TB equal to 3 meters over W, right? So 3 over 23 over 9, which is the initial velocity. So this time is 27 over 23 seconds. So 1 point, what is it, 1.2, something like that, 1.1 seconds. Okay, so let's now find how much distance A will cover during that time. So during TB equals to 27 over 23 seconds, comma, A will cover a distance, of V times TB, which is equal to 17 over 9 times 27 over 23, which yields 51 over 23 meters. Okay, I hope this is clear. So let's keep moving, create a clean page. So A and B are separated by a distance of 3 meters minus 51 over 23, which is equal to 18 over 23 meters when B hits the wall. Okay, so I hope this is clear. So I'm gonna draw another picture which is gonna depict. Okay, so if A is here moving with velocity 17 over 9, okay, and B is right at the wall, okay, so this is the floor, okay, so this is the wall, so that's the wall, that's B moving with velocity 23 over 18. So the moment B hits the wall, A is at the distance of 18 over 23 meters away from B. Okay, and then again, the distance D is going to be the point where these two guys meet. So that's D. So that's going to be B. This is going to be A. Okay. So D is smaller than 18 over 23 meters, in other words. Okay, so let's continue. Okay, so I hope the reasoning is clear so far. So now A, the next step is that A needs to cover 18 over 23 minus D, right? It has to cover this distance. Actually, let's write it like that. So A needs to cover a distance of 18 over 23 minus D in the same time, okay, that B covers the distance D. Okay, so we need another clean page. So we have W prime is going to be D over T. So T is D over W prime. Okay, and similarly, V is going to be 18 over 23 minus D over T. The time is going to be the same. Okay, so T is also 18 over 23 minus D over V. So we have to set these two quantities equal to each other. So D over W prime is 18 over 23 minus D over V. Okay, and we have to solve this algebraic equation now. So we have 18 over 23 times 17 over 9 times D is equal to 18 over 23. So I multiplied V with D over W prime pretty much. Okay, 18 over 23 minus D. Okay, so we have D times 1 plus 34 over 23 is equal to 18 over 23. So D times 57 over 23 is equal to 18 over 23. So we get a nice cancellation. So D is 18 over 57 meters. And that's the answer, okay? This was complicated, okay? I mean, it took me some time to set it up. And okay, I found the answer, but then I was trying to understand. I mean, trying to figure out how to present the result. Okay, and 18 over 57. I think it can be simplified, right? Let me see. Yeah, 6 over 19. So this is also 6 over 19 meters. Okay, so this was a complicated problem, as we said, but we're done with it. And let's move to to question number 7, which is the last question in this test, which is a difficult test, I think. So let's move on. Okay, question 7. In this question, the unit vectors I and j are in a vertical plane, I being horizontal and j being vertically upwards. At time t equal to 0, particle p is projected with velocity 4I plus 9j meters per second from a fixed point O on horizontal ground. The particle moves freely under gravity. When P is at the point H on its path, P is at its greatest height above the ground. Question A, find the time taken by P to reach H. Okay, so let's start working on this. So this question 7. So at t equal to 0, P has an initial velocity, let's call it u naught, okay, which is 4I hat plus 9j hat meters per second, okay. So let's draw the y and x, okay. So that's y and x, and this is a motion under gravity pretty much, okay. So this is the motion, okay. So this is the height that they mentioned, okay. And v should look okay, I'm gonna comment on it in a moment. So that's the initial velocity vector, not the general velocity vector, okay. So this is what I'm trying to explain now, because the general velocity vector has a time dependence, okay. So part A, at the top position, the y component of the velocity should be 0, okay. So if we use suvat, okay, we have vy is equal to uy minus gt. What is uy? It's 9 meters per second pretty much, okay. So yeah, you see that there is a time component there in the problem. Okay, let's undo that, okay. So we have 0 equal to 9 minus gt, so t is 9 over g, and if we plug in numbers, we find 0.92 seconds, since g is 9.81 meters per second squared. Okay, so part A is done. Okay, so let's read. Okay, for part B, we start over there. At the point A on its path, the position vector of P relative to O is ki hat plus kj hat meters, where k is a constant. Part B, find the value of k. Okay, so let's go do that. Okay, so this is part B. Okay, the initial, we called it u naught, right? So the initial velocity vector is 4I hat plus 9j hat meters per second, which means that in general, the velocity vector is going to be 4I hat plus, actually, let me erase that and make it square bracket, okay, plus 9 minus gt j hat, right? Because it's motion under gravity with initial velocity in the y direction equal to 9 meters per second. And then, I mean, that's the Suvat equation, right? Because the Suvat equation is v is equal to u plus at. In our case, we are moving in gravity with initial velocity 9. So vy is 9 minus gt, pretty much, which we wrote there. Okay, maybe this is an overkill a little bit, but I just want you to have the picture clear in your heads. Okay, now we are asked to find k for the position vector, okay. So for vx, we have that vx is 4, right? So in the x direction, actually, maybe it's better to do it this way. Sorry if I'm confusing you. So the Suvat equation is s is equal to ut plus 1/2 at squared, right? So in the x direction, we have x is 4 times t, right? Because that's the initial velocity in the x direction, plus 0, because there is no acceleration in the x direction, okay? Now for the y direction, we have uy is 9 times t minus g over 2 t squared, okay? So this is going to be our general position vector pretty much. So our general position vector is going to be r is 4t I hat, okay, plus 9t minus g over 2, oops, I forgot the t squared, sorry about that, t squared, and then I also forgot the j hat. I'm all over the place, I'm sorry guys. Meters, okay, so that's the general position vector, okay. If r is equal to k I hat plus k j hat, this means that x is equal to y, right? So the x component is 4t, and it should be equal to the y component, which is 9t minus g over 2 t squared, right? And we will do something that will make mathematicians go crazy, but we can delete one of the t's because t is not 0, okay? So we find that g over 2 times t is 9 minus 4 is 5. So t is 10 over g. Okay, let's create another clean page. Now, let me use black. So t is 10j, but we can, so we immediately see that k is 4 times t, right? Equivalently, k is 90. Okay, let's do both so you see that it works. So k is 4 times t. So k is 4 times, what was it, 10 over g. So it's 40g, okay? Because this vector should be equal to this vector, okay? If we use k, if we use the y component at that time, okay, so k should also be equal to 90 minus g over 2 t squared, okay, for t equal to 10 over g. So we will have 90 over g minus g times 100 over 2g squared, right? Yes, okay. And this cancels, so that's 50. So 90 minus 50, also 40. Actually, this is 40 over g, and this is 40 over g as well. Okay, so you see how things work, okay? So k is 40 over g, in other words. Okay, so this was part B. Now let's go see part C. So this is part C. Find, in terms of k, the position vector of the other point on the path of P, which is at the same vertical height above the ground as the point A. Okay, so this requires a little bit of thinking. Okay, so from part A, we know that the particle reaches its maximum height at t equal to 9g. And then we know from part B that at time equal to 10 over g, the particle reaches point A. Okay, so this is the key. So actually, let's write this down. So this is part C. Okay, at t equal to 9 over g, P reaches its maximum height, right? At t equal to 10 over g, it reaches point A, right? This means that point, let's call it A prime, which is at the same height as A, occurs before the particle reaches H. So let's design this. So this is the point A prime that we are looking to find. Okay, so this is the particle, this is the maximum height, and this is point A. Okay, and the height for both above the ground is the same. Okay, so it needs a time of 9 over g to make it to the maximum height. It takes a time of 10. Oops, actually, let's write it over here. So a time of 10 over g to make it to point A. So for point A prime, we will have 10 minus 10 over g minus 9 over g. So this distance is covered in 1 over g. Okay, so 1 over g, not 1 over 9, excuse me. Okay, so this distance will be covered in a time of 1 over g as well. So this time over there is going to be 9 over g minus 1 over g, 8 over g. Okay, so by symmetry, you can kind of figure this out. Okay, I hope this makes sense. Let's create another. Okay, the time needed is 8 over g. So x is 4 times t. So 4 times 8 over g is 32 over g. And since k is 40 over g, this means that g is 40 over k. And in terms of k, x becomes 32 over 40k, which is 4k. So in terms of k, the x component of the position vector is going to be 4k over 5 I hat. And since it's going to be at the same height as point A, for the y component, we will just have k, j hat, just like we had earlier with the other position vector that was ki hat plus kj hat. So the position vector for A was ki hat plus kj hat, right? So yeah, I hope this makes sense. So this was part C, and we are left with part D. Okay, so let's go read part D. So part D is this one. At time t capital seconds, the particle is at the point B and is moving perpendicular to 4I hat plus 9j hat. D, find the value of t capital. Okay, so this is part D. At t seconds, the particle is at B, okay, and perpendicular to 4I hat plus 9j hat, okay. Now the velocity vector is, as we said, okay, remember earlier, I wrote it down and I told you that maybe we will not need it. This is the time we will need it, okay? Now, the velocity vector, okay, sorry if I'm confused, if I'm getting it dizzy. So the velocity vector is 4I hat plus 9 minus gt j hat, right? So since it's moving perpendicular to this vector, the dot product, okay, perpendicular means that v the velocity vector, dotted with 4I hat plus 9J hat is 0, okay? Which means that we have the I components 4 plus 4, so 16, plus 9 times 9, 81, minus 9G, and then T, that's the time we are looking, is 0, okay? Okay, so 9GT is 97, so T capital is 97 over 9G, and if we plug in for G, we find 1.1 seconds. Okay, this was a really long paper, long and difficult questions, I think, okay? But this is it, okay? So this is Mechanics M2 paper, the Mechanics M2A paper from January 2026. Next, I also prepared a Unit 1 physics paper, and after that, I will stop uploading past papers for some time and focus a little bit on theory and other things I want to introduce into the channel. Okay, the channel is growing, but not at the rate that I was hoping for. So please like, subscribe, write your comments. Let me know if these videos are useful, etc. And I'm gonna see you guys in the next videos, okay?